The speed of waves. For this lesson, you will need a timer, a spring scale, measuring tape, and a coiled spring. When looking at waves, there are three important characteristics of a pulse that we can easily control: the height or amplitude, the width or wavelength or period, and the shape or the waveform. We will be varying the pulse in a number of different ways, and we'll observe the speed of the waves. Look at the speed of a regular wave, a wave with long amplitude, short amplitude, a long wavelength, a short wavelength, or an odd shape. From this, you should have observed that the speed of a pulse or wave does not depend on the height, width, or shape. The speed only depends on the physical properties of the medium, such as tension. We will be using a coiled spring to steady the motion of ideal wave pulses. We will be varying tension and seeing how this affects the speed of the wave. Make sure to measure distance and time so that we can calculate the speed. We will be increasing tension by 2 newtons, then 4 newtons, and 6 newtons. We will be starting off with 2 newtons and taking account of the distance and the time. Send a standard pulse through the spring. Mark down the variables and use the basic kinematics equation, speed equals distance over time. We will now look at 4 newtons. We will send a standard pulse through the coiled spring again. Make sure to pay attention to the speed. Then mark down your variables yet again and calculate your speed. Repeat this process for a final time using 6 newtons. At this point in time, you should see a recurring pattern. By looking at this data, we can see that the greater the tension, the faster the speed. Now we will look at how the speed of a wave is related to its frequency and wavelength. This diagram shows a hand which moves up and down with a fixed frequency. We can see that the hand moves 1/4 of a cycle through each picture, as shown on the left. And similarly, between each picture, an additional 1/4 of a wavelength is added, as shown on the right. A wave travels one wavelength in one period. This time, another wave has been generated, but the time taken by the hand has doubled. Since the time taken by the hand is doubled, the frequency will be halved. As well as this, we can see that the wavelength will be doubled. Since the frequency is halved and the wavelength is doubled, the wave speed will remain constant. The red is the initial wave, whereas the green is the second wave. From this, we can see that frequency and wavelength are inversely proportional to one another. If one increases, the other decreases. From our findings, you may have been able to see that the universal wave equation is V equals F lambda, or velocity equals frequency times wavelength. Note that the change in frequency affects the wavelength and vice versa, but they do not affect the wave speed. Remember that the wave speed depends only on the physical properties of the medium.